Hi everybody. This video is intended to be an overview of all nomenclature in chemistry. So the intention is that with this video, if you follow the methods described here, you should be able to look at the formula of just about any compound you encounter and know how to name it. So this is going to work as a sort of flowchart which goes from left to right. So if you want to take this down in your notes, a good way to do it would probably be to turn your notebook sideways. So there are a ton of different chemical compounds out there, and it's really important to be able to name each of them accurately so that when you're talking with other chemists or other students of chemistry, you're all speaking the same language and you all understand what you're talking about. So the way we're going to proceed here is by asking a series of questions, and then depending on the answers to those questions, we will take certain steps to name the compounds. So let's start off here. The first question that you should ask when you're naming a compound is the first element in the name or in the formula of the compound a metal? And what you can do to answer this question is take a look at your periodic table. Now I have a periodic table that's just appeared here that's made all the metals a silvery color and all the non-metals green or a sort of goldish color. So what you can see here is that there's a sort of a staircase divider which comes down like this across the periodic table. If you're to the left of this staircase, then that element is a metal, excluding hydrogen, which is sort of in a special spot. Everything to the right of the staircase is a non-metal. Okay? So when you're looking at the compound, the formula, and you're trying to figure out the name, the first question you're asking is it a metal? And so is it on the left side of this staircase, or is it on the right side of this staircase? That's your first question. So if the answer to that question is no, then the nomenclature actually gets fairly simple. If the answer to that question is no, then you're looking at a covalent compound. A covalent compound. Covalent compounds are defined by the sharing of electrons among the elements in the compound. More on that bonding and how it works and all that will come later. Now we're just worried about naming. So how does this work? Well, if we've said no, the first element is not a metal, it's a non-metal, then the way for setting up the name of the compound is relatively simple. You just say the name of the first element, then you say the name of the second element, but for the second element, you're going to add an ending, which is IDE. So for example, oxygen will become oxide, fluorine will become fluoride, sulfur will become sulfide, and so on. There is one additional thing that we need to add here, and that is a numerical prefix to the beginning of each name for each element. So we need to add a numerical prefix that tells us how many atoms of each element there are in the compound. And so we'll do an example or several examples in a moment that should clarify this further, but for now let's just remember what those numerical prefixes are. For 1, 2, 3, 4, 5, and we'll go up to 10. 6, 7, 8, 9, 10. So for 1, the numerical prefix is mono. For 2, it's di. For 3, it's tri. For 4, it's tetra, like tetrahedron. For 5, it's penta, like pentagon. For 6, it's hexa, like hexagon. 7, hepta. 8, octa. 9, nona. 10, deca. So these are the numbers you'll be using. Now let's take a look at a couple examples of naming covalent compounds to make this really clear. And I'll just make up a couple of them. So how about, let's do N2O4, P3O7, and some of these are probably not even compounds, I'm just sort of picking random things out, CO2 and CO. So N2O4, let's switch to another color. N2O4 would be dinitrogen, tetroxide. Notice we say tetroxide and not tetraoxide. I suppose if you said tetraoxide, it wouldn't be terrible. We tend to say tetroxide just because it sounds better. For phosphorus, P3O7, that's going to be triphosphorus heptoxide. And I've chosen oxides for all of these just so that there's some consistency. This next one you might think would be monocarbon dioxide, but actually we just call it carbon dioxide. That should be a name that's fairly familiar to you. Now, in this naming this element, we see an exception to the rule of covalent compound naming, and that's that if the first element in the compound would have a subscript of 1, that is to say, if there's only one atom of the first element in the compound, we don't include the prefix mono. We clearly do include the numerical prefixes when the number is greater than 1, as in dinitrogen and triphosphorus, but when the number is 1, we don't include mono for the first element. However, this compound here we would call carbon monoxide. So if the second element only has one atom, then we do still use the prefix. So that's the one exception for covalent compound naming. If the first element in the compound, if there's only one atom of that element in the compound, then you don't include the prefix mono. You just say the compound, as in carbon dioxide or carbon monoxide. So, pretty straightforward. If your first element is not a metal, you just say the first element name, the second element name, you add a numerical prefix. If your first element is a metal, then we're going to have a few different branches of the tree here. So let's say, yes, we looked at the compound, we checked the periodic table, it does appear that that first compound is a metal. Well, now you're dealing with an ionic compound. These are compounds which stick together due to the electrostatic attraction between positive and negative in the crystal structure of the compound. If you've answered yes to this question, that the first element is a metal, you should ask a follow-up question. And that should be, is the metal in columns 1 and 2, column 1 or 2, I should say, of the periodic table? Sometimes we'll call this group 1 or group 2. Column 1 or column 2 of the periodic table. And those columns, if we come back down to our periodic table, this is column 1. This is column 2. We call this first column the alkali earth metals, and the second column is the alkali metals and the alkaline earth metals. So the alkali metals on the left, alkaline earth metals, second column. So all of these elements, when they form ions, they have a constant charge which never really changes. So all of these have a charge in the first column, have a charge of +1. Actually, let me pick a different color so that there's a little more contrast there. How about this one? Sure. So all of these have a charge of +1. Whereas all of these in the second column have a charge of +2. So these are all 2+. That's important because a lot of metals, in fact, all these metals in this region here can have variable charges. Sometimes they'll form compounds where they'll have a charge of +1. Sometimes it'll be a charge of +2, +3, +4, +6. There are a lot of different options. But if you're in one of these first two columns, if your compound starts with, say, potassium, which is represented by the letter K, or magnesium, which is represented by the letters Mg, then you know the charge. So let's proceed, assuming that the metal is in column 1 or 2. So we're going to say, yes, we said yes to this question. So now we're looking at ionic compounds where the metal is in the first or second column. So in this case, the naming is relatively straightforward, and all it is basically is the name of the first element, followed by the name of the second element. And as in covalent naming, the second element will also get an IDE ending. And that's basically it. So let's look at a couple of examples here. How about LIF, CABR2, RB3N, and SRO. LIF Well, we would just look at our periodic table. We'll see that's lithium fluoride. So lithium fluoride. And it may take you a little while to find elements on the periodic table, especially as you're beginning. But the more you practice, the better a sense you'll get of the periodic table and the faster you'll become. This one will be calcium bromide. This next one will be rubidium nitride. And the final one will be strontium oxide. Okay, so that's pretty straightforward. If your first metal is in column 1 or 2, then you basically just say the name of the first element followed by the name of the second element. It's really that simple. Now, what if it's not? What if it's in that vast region in the middle of the periodic table? Well, then you're dealing with a transition metal, and things get a little more complicated, but there's still a set of rules you can follow that'll work for you. So if you said no, it's not in those, then you're dealing with a transition metal. And so the rule becomes a little bit different. If you're dealing with a transition metal, and once again, the transition metals are in this middle region of the periodic table here, and also we'd count the lanthanides and actinides down here as well, although I'm not particularly familiar with the chemistry of those elements because you just don't, I haven't studied it very much. I imagine it's pretty similar to the other transition metals in certain ways. In any case, you're unlikely to encounter compounds involving those lanthanides and actinides, so we won't focus on them for now. The rule when you're dealing with a transition metal, which can, remember, change its charge, is that it's exactly the same as it was for the column 1 and 2 metals, except we need to indicate the charge of the transition metal ion in the compound. So the way it'll work is you'll write the name of the first element, name of the first element, and then you'll also have the name of the second element with that IDE ending. But in between, in parentheses, you'll add the Roman numeral for the charge of the metal. So I'll say the Roman numeral of the metal's charge. And I think if we do a couple examples, that'll become a bit more clear. So let's write down a couple examples right here to clarify things. So how about this? We'll do FeO, Fe2O3, CuN, and WO3. So you might ask, if the trouble with transition metals is that they can have multiple different charges, how can we know the charge of the metal just by looking at the compound's formula? Well, as is the case in a lot of problem solving in chemistry, physics, and other science classes, what you need to do is reason from the things you do know to the things you don't know. So for example, let's take this iron oxide here, FeO. What's the charge of the iron? Well, if you remember that in any ionic compound, the sum of the charges needs to be 0, then we can start with the charge of the oxygen and use the charge of the oxygen to determine the charge of the iron. Here's how we do that. So we know the oxygen has a charge of 2-. How do we know that? Well, you may recall that when you look at the periodic table, just as you have positive charges in the first two columns, +1, +2, you have a similar sort of pattern in the non-metal side of things. So let's just fill that in quickly as well so we have that. So we'll use a nice purple here. So this is a 1- charge for this row, which we call the halogens, and then this is a 2-, 2-, 2-, and so on. This is a 3-, 3-, and so on. Okay, so you have that, and that's always going to be the case, almost always going to be the case, and so you can reason from that known information to some unknown information. So if we know the oxygen is 2-, and we know that the iron needs to somehow sum up to 0 with that 2-, well then the iron must be 2+. And that means that this compound is iron 2 oxide. So this number right here, this 2+, becomes the Roman numeral, and that's iron 2 oxide. Well, how about this next one, Fe2O3? It's also made of iron and oxygen, but it's in a different proportion, and it'll have a different name as well. So this time we have 3 oxygens. I'll draw all 3 oxygens. The same 2 minus charge on each. And we also have 2 irons. So the sum of the charges of all 3 oxygens is going to be -6. 2 plus 2 plus 2 is 6, and they're all negative. So the sum of all the oxygens is going to be -6. Well, we've got 2 iron atoms to counter that -6 charge. So what charge should each have in order for the charge of all the iron to add up to +6? The charge on each iron should be +3. If the charge on each iron is +3, then those will sum up to +6. That will exactly neutralize the charge of the oxygen, and that's all you need to do. So this compound would be iron 3 oxide. And notice, this is iron 2 oxide, this is iron 3 oxide. They're different substances and they have different names. This is why it's important to distinguish between the two using these Roman numerals. If someone were to say, hey, would you go get me some iron oxide? As a chemist who understands nomenclature, you would have to clarify and say, which iron oxide? Because there are multiple. When we're dealing with column 1 and 2 metals, that sort of clarification is not needed. If somebody says, get me the lithium fluoride, you know they mean LiF. If they say, get me the calcium bromide, you know they mean CaBr2. But when there are transition metals involved, it's a little bit more complicated. You have to specify which oxide of iron you want. So let's take a look at this copper nitride and this tungsten oxide as well. So for the copper nitride, we have, again, we're starting with what we know. The nitrogen has a charge of 3-, and the copper, well, in order to neutralize that charge, it must have a charge of 3+. So this is copper 3 nitride. Over here, we've got 3 oxygens, 2-, and we have 1 tungsten. So this must have a charge of 6+ in order to counter the charge of all these oxygens, which makes this tungsten 6 oxide. Notice it is important to have a sense of your Roman numerals. If you don't know how to count up to 10 in Roman numerals, I do suggest you look up a list and memorize that so that you have it in your mind. So we actually have the vast majority of nomenclature right here in our hands already. And actually, let me see if I can zoom out and show this whole document. And yeah, there we go. So there it is. It's certainly a lot to know, but it's not impossible. I think you can see that there's a certain flow to naming that if you follow it, you'll be okay. So this is sort of the general rule set. Before we conclude, I do want to spend about 10 minutes including some exceptions and clarifications. So the first thing, which I think is perhaps the most important, is introducing the idea of polyatomic ions. These are things that you're going to see in your compounds quite a bit, and so you ought to be familiar with how to name these. These polyatomic ions are only going to be of interest when it's an ionic compound, so you'll see that the first element is a metal, or it'll be the polyatomic known as ammonium. But let's just take a look, because if we really want to understand this, we'd better start with some examples. So I'm going to zoom back into an empty spot, probably around here, and we can use that to talk about polyatomics. That'll be our little sort of sidebar of polyatomics. So we'll go up here. There we go. And we'll make a little polyatomic ion box for ourselves. There we go. Very nice. Happy little box. So what if you see an element that has more than a compound that has more than 2 elements in it? For example, what if you saw something like this? Or perhaps something like this? Or, I don't know, how about something like this? What would we do with those? So the first thing that you want to look at to determine whether you're looking at a compound with a polyatomic ion is how many elements are there in the compound. If you see more than 2 elements in the compound, then you can pretty much be assured you're dealing with a polyatomic ion when you're looking at ionic compounds. And how do we know how many different elements there are? Well, basically, every element in its symbol has one capital letter. And so what you can do is just count the capital letters in each compound. And so this one has 1, 2, 3 capital letters. So there's a polyatomic ion there. This has 1, 2, 3. So again, a polyatomic ion is present. 1, 2, 3. Again, a polyatomic ion is present. We could even do one more and say NH4NO3. In this case, though there are only actually let me make it so there's more than 3 there. How about NH4 let's just make it NH4CN. There we go. Oh no, the color scheme. NH4CN. Okay, moving on. So this one has 1, 2, 3, 4 different elements in it. Certainly a polyatomic is in there. In fact, 2 are. So how do you know, once you recognize that there's a polyatomic ion, how do you know what its name is? Well, eventually you may have this memorized because of dealing with these compounds a lot. But at first, you can just make reference to a table. So your teacher should give you a table, or possibly there'll be one in your textbook, and you can use that to figure things out. So what you'll do basically is, if you've identified that Cn is your polyatomic ion, you just look at your table and you see something like this. Cn minus equals the cyanide ion. PO4, you'll see in your chart, equals the phosphate ion. CO3, 2 minus, is the carbonate ion. NH4 plus is the common positive polyatomic ion you may deal with. That's called ammonium. And then again we have Cn minus, which is cyanide. Now what you should notice as well here is that, oh whoops, and I made a mistake in writing one of these elements. Now this should be Li3PO4. I was about to say, what you should notice is that the charges in all of these balance. So this calcium has a charge of 2 plus, the carbonate has a charge of 2 minus, so those balance. The ammonium has a charge of 1 plus, the cyanide has a charge of 1 minus, so those balance. Then this is how I noticed that I messed up here. The phosphate has a charge of 3 minus. Lithium, each one only has a charge of 1 plus, so there must be 3 of those to balance the charge of this phosphate group. And then sodium has a charge of +1, cyanide has a charge of -1. So again, the charges balance. So polyatomic ions are just an extension of types of ionic naming. They still obey the rules of ionic naming that we laid out before. One additional note, I'll make a little sidecar on the side of this box here, is a set of polyatomics called the oxyanions. And these are polyatomics that can have variable numbers of oxygens in their name. So I'll label this oxyanions. And so the example that I like to use is chlorate. So ClO3 minus is a polyatomic that we call chlorate. With only 2 oxygens, it has the same charge, and it's called chlorate. With only 1 oxygen, it still has a -1 charge, and we call it hypochlorate. And with 4 oxygens and a 1- charge, we call it perchlorate. So sometimes, so you'll see there's an oxyanion that has an 8 ending, and then these various sort of modifications of that give the compound, or the polyatomic rather, a different little prefix or suffix. So if you add an oxygen to the 8, you get per whatever 8. If you subtract an oxygen, it goes from 8 to ite. If you subtract 2 oxygens, it goes from 8 to ite, and you add the prefix hypo. So again, just to give you another example, maybe you have NO3 minus, which is nitrate. Well, what if you had NO2 minus? That would be nitrite. Okay, so that's the polyatomic sidebar. You're going to do just the same things as you do with all ionic naming, but the polyatomics are sort of special. If you see more than 3 elements in a compound, pull out your chart, look it up, check the charges, check the name, and you're just going to write down the name just the same way you would with any other ionic compound. You never use numerical prefixes with polyatomics. You never say anything like diacetate or tricarbonate or anything like that. Okay, the final thing that I want to add has to do with the transition metals. And that's that there are a couple of transition metals which only very rarely form multiple transition states, multiple oxidation states. That is to say, they mostly always have the same charge. And so even though they're in the zone of the transition metals, actually, let me go down the periodic table to talk about this. Their charge is pretty much always the same. So let's mark those charges in here. So we'll pick a nice blue. And so this aluminum is typically a 3+ charge. I'm going to go a little finer on my brush here. So aluminum is typically a 3+. Gallium, also a 3+. Zinc is a 2+. Silver is a 1+. And those are the ones you'd most commonly encounter here. And so if you can remember just those 4, then you'll be in pretty good shape. And the thing to know about naming is that because these are pretty much always this same charge, you actually don't have to worry about including that charge as a Roman numeral in the name. So for example, if I had ZnCN2, by the way, notice polyatomics, when you have more than one, you put parentheses around them. If you only have one, you don't put parentheses around them. This is zinc. This is cyanide. So all you have to say is zinc cyanide. Oops. Zinc cyanide. You don't have to say zinc 2 cyanide. There is no zinc 3 cyanide or zinc 1 cyanide. Everybody will know what you're talking about if you just say zinc cyanide. So if you have one of these 4 transition metals, and there are a couple others that are sometimes included on these sorts of lists, but we won't worry too much about them right now, then you don't include those Roman numerals in your naming. So let's zoom it on out and survey the scene again. So we've got a series of questions, and I really do, if you're struggling with nomenclature or if you're just starting out with nomenclature, follow this kind of a table. Follow this kind of a process. Actually go through and ask yourself, is the first element a metal? No, it's not. Okay, well then here's how you name it. Yes, it is a metal. Is it in the first column? Yes, it is. Well, okay, then here's how you name it. Oh, it's not in the first column? Okay, no problem. Here's how you name it. And then you check for polyatomics as well, and you check to make sure that you're not including Roman numerals when it's a transition metal that doesn't warrant the use of Roman numerals. If you can practice this sort of flowchart procedure each time as you're starting out, eventually it'll become ingrained in your mind, you'll get really good at the naming, and it'll become just as effortless as it is for you to speak your first language. Okay? So I hope this is helpful to you. If you have any questions, definitely ask your teacher to clarify. Get a lot of practice. The more you practice this, the better you'll be. And we'll see you next time.